In approximately 14,000 days, a probe the size of a grand piano will transmit its last pulse of data across 15 billion miles of empty space. After that, no one will ever know where it goes. Not because we will stop caring, not because the technology to track it will be unavailable, because by the time the last signal dies, Voyager 1 will have outrun every instrument capable of receiving what it sends. The transmitter will still be on, probably. The probe will still be moving, still be spinning slowly through the dark, still be carrying everything it launched with. The silence will not be the silence of a machine that broke. It will be the silence of a machine that has simply travelled too far for its voice to reach. Tonight we map the journey that begins after that silence. It is a strange journey to map. There will be no telemetry, no confirmations, no spacecraft tracking reports from the Deep Space Network, no orbital determination, no trajectory updates. After the last pulse arrives at the antenna in the Mojave Desert or in Spain or in Australia, the probe crosses into a kind of permanent unknowing. We will know where it is going because physics tells us. We will never confirm it got there. But physics tells us quite a lot. Physics tells us which star it will approach most closely, and when, and how close. Physics tells us what the environment is like between here and there, and how that environment changes as Voyager moves deeper into the galaxy. Physics tells us what happens to a gold-plated copper disk sitting in the interstellar medium for millions of years, and which parts of that disk will survive, and which will not. And physics, combined with probability theory, tells us the exact odds that any civilization anywhere will ever intercept Voyager, find it, and understand what they have found. The odds are not encouraging, but the journey is remarkable, and it begins with a countdown that is already running. To begin understanding what that journey looks like, it helps to understand what Voyager actually is. Not the mission, not the discoveries, but the physical object, the hardware, the probe. Voyager 1 weighs 722 kilograms. At launch, with its fuel, it was heavier, but the fuel is long spent. The spacecraft is structured around a central 10-sided aluminum frame that houses the electronics and computers. A large parabolic dish antenna, 3.7 meters across, dominates the structure and is responsible for all communication with Earth. 3 long booms extend from the main body, one carrying the planetary radio astronomy and plasma wave antennas, one carrying the magnetometer, and one carrying the radioisotope thermoelectric generators, set apart from the main body to reduce radiation interference with the scientific instruments. The computers aboard Voyager are a product of 1970s engineering. The flight data system processes scientific data from the instruments. The attitude and articulation control system manages the spacecraft's orientation in space. The command computer subsystem stores and executes commands sent from Earth. These computers were programmed before the mission launched and cannot be easily changed. Minor software updates have been transmitted to them over the decades, but the fundamental architecture is fixed. The onboard computers have a total memory measured in kilobytes. A modern smartphone has roughly 1 million times more processing power, and yet these ancient computers, running code written before personal computers existed, have maintained a spacecraft through the solar system and into interstellar space for nearly 50 years. They have managed the orientation of the antenna through precise thruster firings, keeping the dish pointed toward Earth with the accuracy required to maintain communication. They have cycled instruments on and off, stored data in digital tape recorders, managed the power budget as the RTG output declined, and executed commands transmitted across billions of miles of space with a one-way signal travel time of more than 20 hours. The spacecraft is not merely still functional, it is still doing science. In the 2020s, Voyager 1 was still detecting plasma waves, still measuring the cosmic ray environment, still monitoring the magnetic field of the local interstellar medium. The data it returns is unique. No other probe is as far from the Sun. No other probe is sampling the interstellar medium at this depth. Every measurement Voyager 1 makes in the coming years, before the last signal finally fades, is data that no other instrument can provide. It is, in this specific scientific sense, irreplaceable. That irreplaceability makes the approaching silence more poignant. When the signal dies, it does not die because the scientific value of the data has been exhausted. It dies because the physics of radioactive decay and the geometry of the inverse square law conspire to make the communication chain untenable. The probe will still have something to say. The distance will simply have grown too large for the message to arrive at a detectable strength. Voyager was never supposed to be here. The original mission design was for a grand tour of the outer solar system. The alignment of the planets in 1977 created a rare opportunity, one that occurs only every 175 years, for a spacecraft launched at just the right moment to visit Jupiter, Saturn, Uranus, and Neptune in a single trajectory, using the gravity of each planet to slingshot toward the next. Voyager 2 took that extended tour. Voyager 1 was optimized for a different trajectory, one that brought it closer to Jupiter's moon, Io, and Saturn's moon, Titan, at the cost of a trajectory that slung it out of the plane of the solar system rather than continuing to Uranus and Neptune. This is why Voyager 1 is now above the ecliptic plane, moving at an angle to the solar equator, while Voyager 2 is below the ecliptic. The specific direction of Voyager 1's trajectory was determined by the slingshot angle chosen to visit Titan. That angle, calculated in the 1970s by navigators using instruments that would be considered primitive by today's standards, is the reason Voyager 1 will approach AC plus 793888 rather than some other star in 40,000 years. The trajectory is a chain of consequences reaching from a specific planetary alignment in 1977, through a navigation decision about how closely to approach Saturn, through 50 years of continuous movement, to a point in interstellar space 40,000 years from now, where a probe and a star will share a region of space roughly 1.7 light-years wide. This chain of consequences is itself extraordinary. The same physics that made Titan's gravity useful for trajectory modification is the physics that will govern where Voyager 1 is in the year 42,025. The universe is consistent in this way. The laws that operate at the scale of a spacecraft's proximity to a moon also operate at the scale of a probe's proximity to a star in 40,000 years. The calculations are different in complexity but identical in character. The engineers who designed Voyager's trajectory were not thinking about where the probe would be in 40,000 years. They were thinking about the encounter with Jupiter in 1979. The 40,000-year trajectory is a consequence of their decisions, not a goal. It is a consequence that we are only able to calculate because the physics is deterministic, and because we know the initial conditions well enough. This is one of the most remarkable aspects of the Voyager mission. The degree to which physics allows us to know things about an object we can no longer control, can no longer measure, can no longer communicate with. The last signal ends our ability to gather new information. It does not end our ability to reason about what the probe is doing. Reason, armed with physics and the initial conditions, extends knowledge into the future beyond what any instrument can measure. That extension is the mission briefing, not what Voyager is telling us, what physics tells us Voyager is doing. If this is the kind of mission briefing you want more of, subscribe and stay with the crew. Strap in, we begin. But to understand what Voyager faces after the silence, you first have to understand the silence itself, what ends it, what the last moments of communication actually look like, and what it means that a probe launched in 1977 to study Jupiter and Saturn is still, decades later, the most distant human-made object ever to exist. The silence has a date. Not a precise one. Not a day circled on any calendar at the Jet Propulsion Laboratory. Not a countdown clock in the Mission Control Room in Pasadena. Because the exact moment depends on engineering decisions not yet made, on choices about which instruments to shut down and in what order, on the precise way the power curve intersects the minimum threshold for reliable transmission. But the approximate window is known. The physics is known. And the physics points to the 2030s as the decade in which Voyager 1 will for the last time send anything home. To understand why, you need to understand what is powering it. Voyager 1 does not have solar panels. At the distances it was designed to reach, the Sun provides less than 0.1% of the energy per square meter that it provides at Earth. Solar panels large enough to power the spacecraft at Jovian distances, let alone at interstellar distances, would have been impossibly heavy and fragile. So Voyager was powered, from the beginning, by radioisotope thermoelectric generators, RTGs, 3 of them positioned at the end of a long boom to minimize radiation interference with the scientific instruments. Each RTG contains a stack of plutonium-238 dioxide pellets. Plutonium-238 is not fissile. It does not sustain a chain reaction. It simply decays, steadily and reliably, emitting alpha particles as it does. Those alpha particles are absorbed by the surrounding casing and converted to heat. Thermocouples convert the temperature difference between the hot radioactive core and the cold space environment into electricity. No moving parts, no fuel to exhaust in the conventional sense. Just the steady, patient radioactive decay of plutonium, converting mass into energy at a rate governed entirely by physics. Plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half of the remaining plutonium has decayed, and the power output has halved. At launch in 1977, Voyager's 3 RTGs produced about 470 watts of electrical power. By the early 2020s, roughly 45 years into the mission, the power output had declined to approximately 250 to 260 watts. By the 2030s, it will have dropped further to perhaps 200 watts or below. The power decline itself is not the problem. Voyager has been losing power steadily since launch, and the mission has been managed to match. Instruments have been turned off over the decades as the available power decreased. The first instrument shut-offs happened in the 1990s. Since then, the spacecraft's power management has been an ongoing exercise in triage, keeping the most essential functions alive as the available power slowly narrows. The problem is the receivers. Receiving a signal from Voyager requires the antennas of the Deep Space Network to pick up a transmission of extraordinary faintness. Voyager's transmitter broadcasts at about 22 watts into a dish antenna 3.7 meters across. By the time that signal crosses the 23 billion mile distance to Earth, it has spread so thin that the power arriving at the receiving antenna is measured in femtowatts. A femtowatt is 1/4,000,000th of a watt. The entire received power from Voyager's signal is less than the amount of energy released by a snowflake hitting the ground. The Deep Space Network's 70-meter dishes can detect signals at that power level, but the margin is shrinking in 2 directions simultaneously. The transmitter power is decreasing as the RETG output declines and the remaining power budget for communication shrinks. And the distance is increasing, because Voyager is still moving, still adding miles every hour. The signal that arrives becomes fainter both because the source is weaker and because the source is farther away. At some point, the signal will fall below the minimum detectable threshold, not all at once. The decline will be gradual. First, the data rate will drop. The mission has already reduced the data rate multiple times over the decades, as lower power means fewer bits per second can be transmitted reliably. The early Voyager mission returned stunning images and scientific data at high bandwidth. The current mission returns a trickle of plasma and magnetic field measurements at a bandwidth that would have seemed primitive to the engineers who designed the spacecraft. Then specific instruments will need to be powered down. The mission operations team at JPL has been managing a careful list of what remains powered and what has been turned off. The plasma science instrument was shut down in 2007. The cosmic ray subsystem, the low-energy charged particle instrument, the magnetometer, the plasma wave system, the ultraviolet spectrometer. One by one, the remaining science instruments have been going dark as the power budget tightens. What remains active changes with each engineering review, and the decisions about what to keep alive and what to sacrifice are made not by algorithm, but by people, by scientists and engineers who have devoted careers to a probe launched before many of them were born. What will the last data actually say? The honest answer is that we do not know precisely, because we do not know exactly which instrument will be the last to transmit. But the candidates are few. The most likely is the magnetometer, which measures the direction and strength of the magnetic field in Voyager's immediate environment. It is one of the lowest power instruments aboard. It does not require processing or imaging. It simply measures a field and reports a number. It is the kind of instrument that can be kept alive when almost nothing else can, because it demands almost nothing of the power budget. So the last data packet from Voyager 1 may be a magnetic field measurement. A number, a direction and a magnitude reported from a probe 15 billion or 20 billion miles from Earth, describing the state of the local interstellar medium at a specific moment in time. The measurement will travel from Voyager's antenna to the Deep Space Network at the speed of light. At that distance, the travel time will be more than 20 hours. So when the measurement arrives at the antenna in the Mojave Desert or in Spain or in Australia, the moment it describes will already be almost a day in the past. The scientist reading it will be receiving a message from yesterday, sent from beyond the edge of the solar system. There is one more dimension to the last signal story that deserves attention, the human dimension. The deep space network antennas that have been listening to Voyager for nearly 50 years are among the most sensitive radio receivers ever built. The 70-metre dishes at Goldstone in California, at Madrid in Spain, and near Canberra in Australia can detect signals at power levels that make the word faint seem like an overstatement. The signal from Voyager, by the time it arrives at these antennas, is more than 15 orders of magnitude weaker than the signal emitted by the probe's 22-watt transmitter. It has spread across a sphere whose radius is measured in billions of miles. The tiny fraction of that sphere subtended by a 70-metre dish is all that arrives at the receiver. To put this in human terms, the total power arriving from Voyager 1 at the Deep Space Network is roughly equivalent to the energy a snowflake releases when it hits the ground. Every second. Continuously. And that signal carries scientific data, navigation information, and engineering telemetry about the state of systems on a probe 23 billion miles away. The engineers and scientists who work on the Voyager mission have been doing this for nearly 50 years. Some of them have spent their entire careers on a single spacecraft. There are people at JPL who were graduate students when Voyager launched, and who have devoted decades to interpreting its signals, managing its power budget, troubleshooting its occasional anomalies. The human investment in Voyager is enormous, and it is an investment that will end with the probe's last signal as surely as the probe's own operations will end. There is something worth noting about the specific character of that ending. A spacecraft mission normally ends when it crashes, or burns up in an atmosphere, or stops responding to commands. The mission ended and so did the spacecraft. Voyager's ending is different. The spacecraft will continue after the mission ends. It will be operational or semi-operational, or degraded in ways we cannot specify in advance. But it will be there. Moving, present in the universe, and we will simply not know what happens to it after the signal fades. The silence is not death, it is loss of contact, a different and in some ways stranger kind of ending. The engineers who have spent careers on Voyager understand this. They know that after the last signal, the probe continues. They know that the mathematics tells them where it is going. They know that the answer to whether it survives, whether it maintains structural integrity, whether the golden record remains intact, will never be verified by any instrument on Earth. The probe will be out there, past the reach of knowledge, moving through the interstellar medium in a trajectory that physics has determined, and that we will never be able to confirm. It is the kind of ending that does not feel like an ending. It feels like a disappearance, and then nothing. There is one more calculation worth making before we close the last signal chapter, because it reveals something specific about the character of Voyager's final years. The RTG power decline is not catastrophic, it is gradual, and the mission operations team at JPL has managed the declining power budget with remarkable ingenuity over the decades, developing techniques for squeezing additional useful life out of a spacecraft whose power margin has narrowed to what would have seemed impossibly thin when the mission began. One of the more striking examples, in 2023 the mission team discovered that voltage regulators aboard Voyager 1 had begun to produce corrupted science data. The corrupted data was traced to a degraded chip in the flight data system, a chip that was processing the output of the science instruments before transmission to Earth. The team spent months analysing the problem, eventually finding a workaround that involved routing the data through a different section of the flight data system's memory. The fix required transmitting commands that took more than 20 hours to reach the probe, waiting another 20 hours for the confirmation, and holding collective breath in Pasadena during the 40-plus hours between sending and knowing. The fix worked. Voyager 1 resumed transmitting clean data. This is the human dimension of the Voyager mission that the impersonal physics tends to obscure. The probe is not alone in the interstellar medium, in the sense that no one is paying attention. It is accompanied by a community of scientists and engineers who know it intimately, who have spent careers on it, and who approach each new anomaly with the accumulated knowledge of nearly 50 years of mission history. The people who keep Voyager alive know the probe better than anyone has ever known any spacecraft. They know which components are most likely to fail and why. They know how the probe responds to different command sequences. They know the quirks and the workarounds and the behaviors that are not in the design documentation because they were discovered operationally through experience. When the silence falls, this community will not dissolve. The people who have worked on Voyager will still be here, or their successors will be here, carrying the knowledge of what the probe was and what it is doing. The mission ends, but the knowledge persists. And the knowledge allows the mission briefing that follows, the calculation of where Voyager is going and what it will encounter, to be conducted with the precision that 5 decades of careful measurement and theoretical understanding provides. The science of the last years of the Voyager mission is not simply diminishing returns. It is the science of a boundary, of an environment that no other instrument has ever sampled, of conditions that are unique to the specific region of the interstellar medium that Voyager is crossing. Each measurement returned before the final silence is the last measurement that will be made by a human instrument in that specific region of space, probably for a very long time. Not because the magnetometer stops working, probably because the RTG output has dropped below the threshold required to operate the transmitter at a detectable power level, or because a system failure elsewhere in the spacecraft has interrupted the power chain, or because a software error in the aged onboard computer, running code written in the 1970s, has corrupted the transmission system in a way that cannot be diagnosed or corrected from Earth. The reasons for the silence will likely never be known. The probe is too far away, the signal too faint, and by the time the silence begins, the ability to diagnose its cause will have eroded along with the signal itself. What will Voyager be doing at that moment after the silence falls? The same thing it has been doing since September 1977. Moving outward. At a velocity of approximately 38,000 miles per hour relative to the Sun, which translates to about 10.6 miles per second, which translates to about 1 million miles per day. The silence does not slow it. The silence does not change its trajectory. Nothing in its environment has the mass to meaningfully deflect it over the timescales we are considering. It will simply continue, in the direction physics pointed it nearly 50 years before, at a speed it cannot change and that no force it encounters will significantly alter. The direction is roughly toward the constellation Ophiuchus, toward the solar apex, the point in the sky toward which the Sun is moving relative to the local standard of rest. But Voyager is not moving directly toward any particular star. It is moving between stars through the space between them, in a direction that will bring it closer to some and farther from others over the next thousands of years. The silence on Earth will be permanent, but Voyager will not know it is silent. It has no way of knowing that. It will continue to operate in whatever degraded state it occupies at the end, as long as some residual power from the decaying RTGs flows through its circuits. The transmitter may continue to broadcast at power levels too low to detect from Earth for years or decades after the last detectable signal. The probe will be sending messages that no one can hear, into a darkness that does not answer, at speeds that cannot close the gap that has opened between it and the civilization that built it. It is, in a particular sense, still ours. And then, by any meaningful measure, it is not. The close is also an open. It is an open because Voyager's departure is not a conclusion but a beginning. The scientific mission, in the traditional sense of returning data that human scientists analyze and publish, is concluding. The other mission, the longer and stranger and more speculative mission of carrying evidence of human existence into the interstellar medium, has barely begun. 47 years of travel has put Voyager 1 at approximately 158 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun. Voyager is 158 times that distance. Expressed in light travel time, it is about 22 hours. In the context of reaching the nearest star, which is 4.24 light-years away, Voyager has covered roughly 0.07% of the distance to Proxima Centauri in 47 years of continuous travel. At that rate, the journey to the nearest star would take about 73,000 years. This puts the probe's position in a specific context. It has travelled an enormous distance by human standards, farther than any human-made object in history. It has reached the interstellar medium, the space between the stars, but on the scale of the stellar distances it must traverse to reach any other star it has barely started. The probe's journey, after the last signal, is measured not in years but in millennia, and then in millions of years. The timescales that become relevant are not the timescales of human institutions or human memory. They are the timescales of geology, of evolution, of the slow churning of stellar populations through the galactic disk. The 40,000 years to the AC plus 793888 flyby is longer than all of recorded human history. The millions of years to the Sirius encounter are longer than the existence of Homo sapiens as a species, and yet Voyager will be there. Not knowing it is there, not caring. Simply present, in the interstellar medium, moving in the direction that physics pointed it when it left the solar system nearly 5 decades ago, carrying its golden record, carrying its decaying RTGs, carrying the physical evidence of a civilization that existed, that built things, that asked what it should say to the universe and then said it. There is something specifically strange about the timescale of the golden record's potential longevity compared to the timescale of human history. The record was designed, as Sagan said, to last 1 billion years. Humanity has existed for 300,000 years. Written civilization has existed for 6,000 years. The United States, the country that funded and built Voyager, has existed for fewer than 250 years. The scientific community that designed the golden record, the late 20th century international physics and astronomy community, has existed as a coherent institution for perhaps 200 years. 1 billion years is to 200 years what 200 years is to a nanosecond. The record will outlast its creators by a factor so large that comparison becomes meaningless. It will outlast, in all probability, any recognizable descendant of the civilization that created it. It will outlast, possibly, the species that created it. It will persist as an object in interstellar space long after every human record, every library and database and hard drive and stone inscription has been destroyed by the geological and astronomical processes that reshape habitable worlds over geological time. The golden record is in this precise sense the most durable artifact in human history, not because it was designed to be, because it was placed in an environment, the interstellar medium, where the processes that destroy things on Earth, oxidation, biological decay, geological transformation, are simply absent. The record persists because there is nothing out there to destroy it quickly. Only the slow cosmic ray sputtering and the very occasional micrometeorite impact, neither of which is fast by any reasonable measure. This is the thing that Sagan understood that is easy to lose sight of in discussions of Voyager's scientific legacy. The scientific legacy will eventually be superseded. Future probes will go farther, carry better instruments, return more data. The heliospheric measurements that Voyager has made will be contextualized by the measurements of future interstellar probes. The data Voyager returns will remain in the scientific record but will not remain at the frontier of knowledge. But the golden record is not a scientific instrument. It is a statement. And statements are not superseded by better measurements. They persist as statements. What the record says about humanity in 1977 will still be what it said, even if no one ever reads it. The act of saying is not made meaningless by the absence of a reader. It is made meaningful by the act itself. That is a point about human consciousness and human civilization that the mathematics of interception probability does not touch. The probability of interception is very low. The significance of the act of making the record and launching it is not determined by the probability of interception. It is determined by what the act reveals about the kind of mind that performed it. The silence falls, Voyager moves on, and the environment it is moving through is stranger than most accounts suggest. We speak of interstellar space as though it were nothing. Empty. The void between the stars. A vacuum so perfect that nothing could matter less about its specific character or composition. But interstellar space is not nothing, and the specific character of the medium Voyager is passing through has been one of the most interesting discoveries of the extended mission. In 2012, after nearly 35 years of flight, Voyager 1 crossed the heliopause. That is the boundary where the solar wind, the continuous outflow of charged particles streaming from the Sun, gives way to the interstellar medium proper. On the inner side of the heliopause, space is dominated by solar particles. On the outer side, it is dominated by particles from the galaxy. The heliopause is not a sharp line. It is a dynamic, irregular boundary, shaped by the magnetic fields on both sides and by the varying intensity of the solar wind over the Sun's 11-year activity cycle. But crossing it was real. The instruments aboard Voyager detected the change. The density of charged particles increased. The direction of the local magnetic field shifted. The cosmic ray environment changed character. Data accumulated over years was analysed, debated, and eventually confirmed. Voyager 1 was in interstellar space. What is that space actually like? The solar system sits inside a structure called the local bubble. It is not a bubble in any physical sense. It is a region of the interstellar medium where the gas density is much lower than average. For most of the Milky Way, the average density of interstellar gas is perhaps 1 atom per cubic centimetre. Inside the local bubble, the density is roughly 100 times lower, about 0.01 atoms per cubic centimetre, almost nothing compared to almost nothing. The local bubble was carved out by a series of supernova explosions that occurred roughly 10 to 20 million years ago. When a massive star dies in a supernova, it releases roughly 10 to the 44th joules of energy in a fraction of a second. Most of that energy goes into neutrinos, but the fraction that goes into kinetic energy of the expanding shell of stellar material is still enough to sweep a cavity through the surrounding interstellar medium hundreds of light years across. The local bubble is that cavity, created by supernovae that exploded before the dinosaurs walked the Earth, and still persisting because the interstellar medium inside it has not yet been replenished. The Sun entered the local bubble roughly 5 million years ago. Homo sapiens did not exist then. Our ancestor species were just beginning the evolutionary transitions that would eventually produce us. The solar system has been travelling through this anomalously low-density region of the galaxy for 5 million years, and it will continue to do so for at least another few million years before eventually crossing the bubble's boundary into denser material. Within the local bubble, the solar system sits inside a smaller structure called the local interstellar cloud, or sometimes the local fluff. It is a cloud of warm, partially ionized hydrogen and helium, denser than the interior of the bubble, but still thin by most standards, roughly 0.3 atoms per cubic centimetre. The cloud extends perhaps 30 light-years across, and the solar system entered it relatively recently, within the last 100,000 years. Whether the solar system will exit the local fluff before the next million years pass is uncertain. The cloud's boundary is not precisely mapped. Voyager 1 is currently inside the local fluff. As it moves outward, it will eventually exit the cloud into the interior of the local bubble again, where the density drops back to the 100th of an atom level. That transition will not be detectable by any instrument on Voyager, because the instruments will long since have gone dark. But the transition will happen. The environment Voyager travels through will change slightly, as it moves from one region of the local interstellar medium to another. The magnetic field structure of the interstellar medium is another feature of Voyager's environment that will change over time. The interstellar medium is permeated by a weak magnetic field generated by the motion of charged particles throughout the galaxy over billions of years. The field is not uniform. It varies in direction and strength on a variety of scales, from parsecs to kiloparsecs. As Voyager moves through different regions of this field over thousands and millions of years, the orientation of the field relative to its trajectory will shift. The field strength is tiny by any everyday standard, a few microgauss. The Earth's magnetic field is roughly 50 microgauss at the surface, so the interstellar magnetic field is 10 to 20 times weaker than the field we experience standing on the ground. But the interstellar field is significant because it governs the propagation of cosmic rays through the galaxy, because it shapes the dynamics of stellar winds and supernova remnants, and because it represents a form of energy and pressure that fills the interstellar medium everywhere. Cosmic rays are themselves one of the most important features of Voyager's interstellar environment. They are not rays in the usual sense. They are high-energy subatomic particles, mostly protons, accelerated to enormous velocities by astrophysical processes, particularly the shock waves of supernova remnants and possibly by the jets of active galactic nuclei and other energetic sources. They fill the galaxy essentially uniformly, with a spectrum of energies extending from millions to billions to trillions of electron volts. At the highest energies, a single cosmic ray proton carries more kinetic energy than a professional baseball hit at full speed, packed into a particle with a mass of less than 2/billionths of a billionth of a billionth of a kilogram. Voyager has been measuring the cosmic ray environment since launch, and its observations of the transition from the solar-dominated environment inside the heliopause to the galactic cosmic ray environment outside have been among the most scientifically valuable results of the extended mission. Inside the heliopause, the solar wind modulates the galactic cosmic rays, deflecting and decelerating them, so that the cosmic ray flux inside the heliosphere is lower than the interstellar flux for particles below a certain energy. Outside the heliopause, the full galactic cosmic ray flux is present. After the silence, Voyager continues to travel through this cosmic ray environment. The particles cannot be deflected by a shuttered science instrument. They pass through the probe continuously, knocking atoms loose from surfaces, depositing energy in whatever materials they encounter, slowly and relentlessly doing the kinds of damage that radiation does to any physical object over long periods. Over the next 100 years, this damage is negligible. Over 1,000 years, it begins to accumulate in detectable ways. Over 1,000,000 years, it becomes significant. Over 1 billion years, it transforms the probe's surface layers profoundly. The cosmic ray environment is not a dramatic hazard on any human timescale. On interstellar timescales, it is the medium's primary mechanism for modifying the physical structure of whatever passes through it. The solar system itself is remarkable when seen from the perspective of what surrounds it. The heliosphere, the bubble of solar wind inflated by the sun's continuous outflow of charged particles, is not a sphere. It is more like a comet, with a roughly spherical shape on the side facing the direction of the sun's motion through the interstellar medium, and a long extended tail on the other side stretching for perhaps hundreds of astronomical units in the downstream direction. The solar system is moving through the local interstellar medium at roughly 20 kilometers per second relative to the local standard of rest, and this motion shapes the heliosphere the way a boat's motion shapes its wake. Voyager 1 exited the heliosphere on the upstream side, the side facing the direction of the sun's motion, where the heliosphere is compressed by the ram pressure of the interstellar medium and has a sharper, more defined boundary. The heliopause on this side sits at about 120 astronomical units from the sun. On the downstream side, the tail of the heliosphere extends much farther, perhaps 1,000 astronomical units or more. From outside the heliosphere looking back, the sun would appear as a slightly brighter star among the thousands visible with the naked eye. Its heliosphere would be completely invisible. The entire extent of the sun's influence, the bubble of solar wind that contains all 8 planets, and all the asteroids and comets and dwarf planets, and everything else in the solar system, is too diffuse and too vast to see as a distinct object from any reasonable interstellar distance. From 4 light-years away, from the distance of Proxima Centauri, the sun is just another star. The entire solar system fits within a volume of space smaller than the resolution of any telescope that could observe from that distance. This is the scale inversion that interstellar space enforces. Everything we know, everything humans have ever seen and touched and studied, everything within the heliosphere is invisible from interstellar distance. The solar system is not large. It is large only within a perspective defined by human scale. From the perspective of the galaxy, it is a point. Voyager is also a point moving through the interstellar medium at a speed that is fast by human standards and slow by galactic standards. A point that we can track as long as it transmits, and that we will lose track of the moment it goes silent. The interstellar medium that Voyager is travelling through has a specific texture that varies on scales of light years. The local bubble, with its anomalously low density, contains several smaller structures called cloudlets, dense patches of material that move through the bubble interior. Voyager will spend the next tens of thousands of years crossing one or more of these cloudlets. The crossing will not be abrupt or dramatic. The density changes are gradual on the scale of Voyager's size, but over thousands of years, the cumulative exposure to slightly different particle environments and slightly different magnetic field configurations will vary as the probe moves from one cloudlet to another. This is not the uniform, featureless void of popular imagination. It is a structured medium with a complex spatial distribution, shaped by millions of years of stellar winds and supernova explosions, and the slow stirring of the galactic magnetic field. Voyager is not travelling through nothing. It is travelling through a history of violence and energy and death and renewal, written in the spatial distribution of plasma and magnetic fields and cosmic rays across the nearest few thousand light-years of the Milky Way disk. And Voyager is, in this context, extraordinarily small. It is smaller relative to the medium it is crossing than a bacterium is relative to the ocean. It is unaware of its environment in the way that a stone is unaware. It simply passes through. As Voyager moves away from the solar system, it is also moving through a region of the galactic disk where the properties of the interstellar medium are not constant over long timescales. The galaxy is not a static object. It is rotating. Stars orbit the galactic center at varying speeds depending on their distance from it. The Sun, at 26,000 light-years from the center, completes one orbit in about 225 million years. In 40,000 years, the time it takes Voyager to approach the star we will discuss shortly, the Sun will have moved a noticeable distance around the galactic center. Voyager, moving much more slowly than the stars but in a direction that is not aligned with the Sun's orbital motion, will have drifted into a slightly different part of the local stellar neighborhood. The Oort Cloud adds another layer to this picture. The Oort Cloud is a vast, roughly spherical distribution of icy bodies that surrounds the solar system at distances ranging from a few thousand to perhaps 100,000 astronomical units from the Sun. It is the reservoir from which long-period comets are occasionally perturbed into the inner solar system by passing stars or by the gravitational tides of the galaxy. Voyager 1 will enter the Oort Cloud in roughly 300 years. Not the inner edge of the cloud, which is warmer and more dynamic, but the outer haze of loosely bound icy bodies that extends well into what we normally call interstellar space. It will be inside the cloud, technically, for roughly 30,000 years. It will then exit through the far side into the deeper interstellar medium that extends between the solar system and the next stellar system. The Oort Cloud is so diffuse that Voyager will not encounter any of its constituent bodies. The probability of a direct collision with an Oort Cloud object during the 30,000-year transit is vanishingly small. The cloud is vast, but its population of objects is spread through an even vaster volume of space, and the cloud is defined by gravitational association with the Sun, rather than by physical proximity of its members to each other. Voyager will pass through without incident, as a ghost through walls. The heliosphere's boundary, the heliopause, is not a fixed location. It breathes with the solar cycle. Every 11 years, the Sun's activity varies from solar minimum, when the solar wind is relatively weak and steady, to solar maximum, when the solar wind is stronger and more variable. This variation in solar wind pressure changes the size of the heliosphere. At solar maximum, the heliosphere is slightly larger. At solar minimum, it is slightly smaller. The heliopause oscillates in and out by perhaps a few astronomical units as the solar cycle plays out. From outside the heliosphere, this oscillation would be invisible, but it is real, and Voyager has measured evidence of it. The Voyager 1 data showed that the transition region around the heliopause is not a sharp boundary, but a zone where the solar and interstellar influences overlap in complex ways, with the dominant contribution switching back and forth over timescales related to the solar wind variability. As Voyager moves deeper into the interstellar medium, the Sun's influence fades. The solar wind, which has already been unable to push beyond the heliopause, exerts no direct influence on the probe. The Sun's gravitational pull continues to decelerate Voyager very slightly, by an amount that is calculable, but very small. The solar light pressure, which at Earth's distance exerts a tiny but measurable push on sunlit surfaces, is negligibly small at Voyager's distance. For practical purposes, Voyager is already in freefall through the galactic gravitational potential, subject only to the gravity of the galaxy and the occasional passing star. The cosmic rays that Voyager encounters in the interstellar medium are galactic in origin. They were produced by supernova explosions, by the shock waves that accelerate particles to relativistic energies as the supernova blast wave expands into the surrounding medium. Those particles then propagate through the galactic magnetic field, bouncing off irregularities in the field and gradually diffusing through the galaxy. The cosmic rays Voyager encounters might have been accelerated by a supernova that exploded millions of years ago on the other side of the galaxy, and have been propagating through the galactic magnetic field ever since. There is something profoundly impersonal about this environment. The cosmic rays do not know that Voyager is there. The galactic magnetic field is not modified by the probe's presence. The local interstellar medium does not record the probe's passage. Voyager moves through the interstellar medium the way a photon moves through empty space, present, real, physical, and completely invisible to its surroundings. What is remarkable is that we can calculate this presence with such precision. The probe is beyond direct measurement, beyond communication, beyond any form of direct observation. And yet physics tells us it is there, tells us approximately where, tells us what it is flying through and at what speed. The knowledge extends beyond the measurement. This is what theoretical physics does at its best. It reaches into places where observation cannot go. What Voyager will encounter over all of these thousands and millions of years is primarily the interstellar medium itself. The cosmic rays, the magnetic field, the thin gas, the even thinner dust, and occasionally, and over long enough timescales inevitably, the gravitational influence of the stars it passes near. In approximately 40,000 years, Voyager 1 will make the closest approach to any star it will ever make. The star's name is AC plus 793888. It is also catalogued as HIP 89825 in the Hipparcos catalogue of stellar positions and parallaxes. It is a red dwarf star, spectral type M4.9, meaning it sits near the cool end of the red dwarf range. It is dimmer than Proxima Centauri. It is dimmer than almost every star visible to the naked eye. In the present-day night sky, it is invisible without a telescope, and even with a small telescope it is a faint smudge rather than a point of brilliance. It sits in the constellation Camelopardalis, the giraffe, a large but obscure northern constellation that contains no bright stars and that most amateur astronomers have never deliberately sought out. In the current epoch, AC plus 793888 sits about 17.5 light-years from the Sun. It is one of our closer neighbours in the stellar census, but not among the closest. It is not a candidate for interstellar exploration in any near-term or medium-term sense. It is simply one of the hundreds of billions of ordinary, unremarkable red dwarf stars in the Milky Way. In 40,000 years, it will pass within about 1.7 light-years of Voyager 1. This requires some explanation, because the meeting of Voyager and AC plus 793888 is not a matter of Voyager travelling toward the star. Voyager is moving approximately toward Ophiuchus, not toward Camelopardalis. A C plus 793888 is moving through the galaxy on its own trajectory, as all stars do, orbiting the galactic centre at its own speed and in its own direction. The geometry of these two motions, the probe moving outward through the interstellar medium and the star moving along its own path through the stellar neighbourhood, will bring them into proximity around the 40,000-year mark. Closest approach does not mean collision. 1.7 light-years is not close by any standard a human being would apply to the concept of proximity. It is roughly 40% of the current distance from the Sun to Proxima Centauri. It is a distance that light takes about 1.7 years to cross. At Voyager's current speed, Voyager would take about 30,000 years to travel 1.7 light-years. So the closest approach is close only in the cosmic sense of close. Two objects that share a region of space roughly 1.7 light-years wide for a period of thousands of years centered on the moment of closest approach. From Voyager's perspective, if we can use that phrase for an object that has long since stopped observing anything, the flyby will be imperceptible. The probe has no instruments to detect the star. Even if it did, a star at 1.7 light-years distance would appear bright by the standards of the background, brighter than Venus in our night sky perhaps, but not illuminating the probe's surface with any meaningful flux of energy. There is no gravitational interaction worth calculating. A red dwarf star of AC plus 793888's mass has a gravitational influence that, at 1.7 light-years, amounts to a gravitational acceleration of roughly 10 to the negative 15 meters per second squared. For context, Earth's gravitational acceleration at the surface is 10 meters per second squared. The star's gravitational pull on Voyager at closest approach is roughly 15 orders of magnitude weaker than the force holding you to the ground. It will not measurably deflect the probe's trajectory. It will not slow it or accelerate it by any amount that would change the subsequent trajectory in any significant way. The stellar neighbourhood changes on timescales of thousands of years in ways that would be bewildering to any observer living on a human timescale. The stars in the Sun's neighbourhood are not fixed. They orbit the galactic centre, each on its own trajectory, at velocities that differ by tens of kilometres per second from one star to the next. The result is that the neighbourhood is in constant slow flux. Stars that are currently neighbours will be separated by dozens of light-years in a million years. Stars that are currently distant will have moved into the local neighbourhood. The constellations we see in our sky, the patterns that human cultures have named and used for navigation for thousands of years, will be completely unrecognisable in 100,000 years as the stars drift apart on their individual galactic orbits. This stellar flux is what makes the Voyager trajectory calculation interesting. The probe's path is determined by physics, but the stars it encounters are determined by the same physics applied to the stellar motions. The calculation of AC plus 793888 as the closest stellar approach in approximately 40,000 years required knowing not just Voyager's trajectory, but the proper motion and radial velocity of AC plus 793888, extrapolated forward 40,000 years. The proper motion of a star is its motion across the sky as seen from Earth, measured in arcseconds per year. The radial velocity is its motion toward or away from us along the line of sight, measured by the Doppler shift of its spectral lines. Both of these measurements have been made for AC plus 793888 with reasonable precision. The uncertainties in the stellar motion propagate into uncertainties in the predicted closest approach, distance and time. The 1.7 light-year figure and the 40,000-year figure are best estimates, not precise predictions. The actual closest approach might be slightly closer or slightly farther, slightly sooner or slightly later. But the existence of the close approach is not in doubt. The geometry works out to bring these two moving points, the probe and the star, into closer proximity than any other encounter in the relevant time frame. And the encounter, while not close in any practical sense, is still the closest thing to an event that Voyager will experience in its long trajectory through the interstellar medium. After a C plus 793888 and Ross 248, the next deep future stellar encounters for Voyager are more speculative. The further you project into the future, the more uncertainty accumulates in the stellar proper motions. Stars whose motions are known precisely enough to predict their positions in 40,000 years become less predictable at 400,000 years, and quite uncertain at 4 million years. The Sirius encounter at roughly 4 million years is a rough prediction, not a precise one. Whether Voyager passes within 2 light-years of Sirius or within 5 light-years depends on small errors in the current measurements of Sirius's velocity that we cannot eliminate with current technology. What we can say is that in 4 million years, Voyager will have traversed a distance of roughly 137 light-years from the solar system, assuming its current trajectory and speed remain unchanged. At that distance, it will be in a part of the Milky Way disk that is entirely unfamiliar to us. The stars in that region are stars we have catalogued from Earth, but they are not stars we have studied in detail. They are points of light in a sky that humans no longer look at from the same vantage point. And in tens of millions of years, the trajectory becomes purely probabilistic. We can describe a probability distribution over where Voyager might be, shaped by the accumulated uncertainties in all the gravitational perturbations it has experienced over its long journey. The probe is still in the Milky Way. It has not escaped. The galactic escape velocity at the solar system's distance from the centre is roughly 550 kilometers per second, and Voyager is moving at roughly 17 kilometers per second. It will orbit the galaxy, very slowly, for billions of years. But the specific orbital parameters will be modified by gravitational encounters with passing stars in ways that will eventually make the trajectory completely unpredictable. The probe enters, in cosmological time, the category of galactic flotsam, debris drifting through the disk of the Milky Way, slowly modified by gravitational nudges from passing stars, orbiting the galactic centre on a trajectory that changes slowly over hundreds of millions of years. The flyby is a mathematical event, a moment in the probe's trajectory where the distance to a specific star reaches a local minimum and then begins increasing again. Voyager will not know it happened. The star will not know Voyager passed. The interstellar medium between them will not be disturbed, but we can calculate it. And there is something worth sitting with in the calculation. In 40,000 years, the civilization that launched Voyager will be, if it still exists, 40,000 years older than it is today. 40,000 years ago from the present moment, anatomically modern humans were in the middle of the Upper Paleolithic. Cave paintings at Lascaux were 10,000 years in the future. The last common ancestor of Mesopotamian farmers and Amazonian hunter-gatherers was only a few thousand years distant. The entire arc of written history, all the civilizations and empires and revolutions and technologies and scientific revolutions, was 40,000 years in the future. In 40,000 years, the gap between the present moment and the cave paintings of the Paleolithic will recur. What exists on the other side of that gap, in the culture and technology and social organization of whatever descendants humanity has, or whatever other forms of intelligence have replaced or evolved from us, we cannot predict in any useful sense. The gap is too large, and yet we can calculate precisely where Voyager will be, and that it will pass within 1.7 light-years of AC plus 793888, because physics does not care about 40,000 years. The trajectory is determined now by the velocity and position of the probe and by the masses and velocities of all the objects whose gravitational influence matters. None of those things will have changed significantly in 40,000 years. The probe will be where the equations say it will be, when the equations say it will be there, with a precision that does not erode with time. The encounter with AC plus 793888 is interesting, for one more reason that goes beyond the geometry of closest approach. A star at 1.7 light-years distance, even if it has planets, is in a specific relationship to any civilization that might exist on those planets. It is close enough to be a bright, distinctive object in the sky, brighter than any star visible to the naked eye from Earth, except for the Sun itself. It is close enough that light from the star takes less than 2 years to arrive. It is far enough that any signal sent to that civilization would take 1.7 years to arrive and another 1.7 years for a response to return. For a civilization that had developed astronomy but not radio communication, a star 1.7 light-years away would look like a brilliant blue-white point of light, second only to its own sun in brightness. They would know it was close, because parallax measurements would quickly establish that it was within a few light-years rather than thousands. They might study its spectrum and determine that it is a G-type main-sequence star. They might determine that it has planets by detecting gravitational wobble in its motion across the sky. In 40,000 years, if there is a civilization on a planet around AC plus 793888 that has reached the technology level at which we would have a chance of detecting each other, they might already have noticed our sun. They might already be wondering whether that nearby G-type star has anything interesting around it. They might already be pointing their equivalent of radio telescopes toward our solar system. In 40,000 years, they would receive signals from us. Not the signals we're sending today. Signals that will leave Earth in the next few years, or that have already left. Signals that are currently crossing the 17.5 light-years between Earth and AC plus 793888 at the speed of light, and that will not arrive for another 17,500 years minus whatever time they have already been in transit. Voyager will pass within 1.7 light-years of this civilization, if it exists, in approximately 40,000 years. The civilization will have received our radio signals roughly 22,500 years before Voyager passes by. If they spent 10,000 years developing the technology to send a probe into interstellar space, and launched that probe toward our solar system in response to our signals, that probe would still be in transit when Voyager makes its closest approach to their star. This is the specific geometry of interstellar communication over astronomical timescales. Everything is delayed. Everything is sequential. The signal we sent long ago arrives long after we sent it. The response we might receive long after that. The physical artifacts in between, like Voyager, are moving so slowly compared to light that they arrive orders of magnitude later than the signals. In this context, Voyager's closest approach to AC plus 793888 in 40,000 years is not a contact event. It is a cosmic coincidence, the intersection of a probe's trajectory with a star's position at a specific moment in the vastly slow ballet of stellar motions through the galactic disk. After the AC plus 793888 flyby, Voyager continues. The next notable stellar encounter in its trajectory is roughly 296,000 years from now, when it will pass within 0.93 light-years of Ross 248, a red dwarf in the constellation Andromeda, somewhat closer than the AC plus 793888 encounter, but still astronomically distant. Ross 248 is slightly closer to the Sun than AC plus 793888, currently about 10.3 light-years away. By the time Voyager makes its closest approach to Ross 248, the star will have moved into a different part of the stellar neighbourhood, and the geometry will place it just under a light-year from the probe's path. After that, in roughly 4 million years, Voyager will pass within a few light-years of the Sirius system, the brightest star in our night sky. Sirius, a hot, bright A-type star and its white dwarf companion, will have moved significantly from its current position in 4 million years. The current closest star to us, Proxima Centauri, will not be near Voyager's trajectory over these timescales in any particularly close way. What is remarkable about all of these encounters is what they are not. They are not close passes. They are not gravitational interactions of any significance. They are not contacts of any kind. They are simply the moments in Voyager's trajectory when the distance to a specific star reaches a local minimum. Milestones without anyone to observe them. Passages through the geometry of a slowly evolving stellar neighbourhood, recorded in the mathematics and nowhere else. There is one more thing worth noting about the 40,000-year flyby. ACPLUS 793888 is a red dwarf. Red dwarfs are the most common type of star in the galaxy. They make up roughly 75% of all stars in the Milky Way. They are individually faint and invisible to the naked eye at anything beyond a few light years, but collectively they are the galaxy's dominant stellar population. They are old. Many of them have been burning steadily for longer than the Sun has existed. Some of them have been burning for longer than the solar system has been around. Red dwarfs are also the most common hosts of confirmed exoplanets. The TRAPPIST-1 system, with 7 rocky planets including 3 in the habitable zone, orbits a red dwarf. Proxima Centauri b, the potentially habitable planet around our nearest stellar neighbour, orbits a red dwarf. The universe, if it contains inhabited worlds, is likely to contain a disproportionate number of them around red dwarfs, simply because red dwarfs are so numerous. We do not know if ASI plus 793888 has planets. Its distance and faintness make it a difficult target for current exoplanet detection methods. But red dwarfs of its type frequently have planets, and some of those planets orbit in the habitable zone, closer to the star to compensate for its lower luminosity. Voyager will pass within 1.7 light-years of a star that might have planets. Might have a habitable zone. Might have, in some extreme speculative scenario, life. And it will pass in silence, without instruments, without the ability to detect or be detected, at a distance that makes even light take nearly 2 years to cross. The flyby is not a contact, but it is the closest thing to a contact that Voyager will ever make after the last signal dies. And it is worth knowing about. Voyager 1 carries a disk, a 12-inch gold-plated copper disk, mounted in a protective aluminum jacket on the exterior of the spacecraft. It contains 116 images, greetings in 55 languages, sounds of Earth including whale songs and thunder, and a mother's first words to a newborn, 90 minutes of music from a dozen cultures, and the sounds of a world that a probe the size of a grand piano left behind in 1977 and has been moving away from at 10 miles per second ever since. The Golden Record was designed by a committee chaired by Carl Sagan. The images were chosen to convey human biology, human society, human geography, and something of the character of the civilization that built the probe. The music was chosen to represent the emotional and aesthetic range of human musical expression. The greetings were recorded by speakers of languages from Akkadian to Wu Chinese. The sounds included rain and wind and surf and footsteps, and the first cry of a child and the hum of a tractor. A stylus was included etched into the aluminum cover, along with diagrams explaining how to play the record and pictures, explaining how to decode the images encoded in it. It was and remains the most ambitious message in a bottle in human history. The bottle is now more than 23 billion miles from the shore it was launched from. And the question that Sagan's committee thought about, and that physicists and material scientists have thought about since, is, what happens to it? What is the physical condition of the Golden Record after 1,000 years of interstellar travel? After 1 million? After 1 billion? The disk itself is made of copper, electroplated with gold. Gold is chosen because it is chemically inert. It does not corrode. It does not react with oxygen because there is no oxygen in the interstellar medium. It does not react with water because there is no water. The chemical hazards of the interstellar medium are essentially zero. Gold will not dissolve, will not rust, will not tarnish, will not react with anything the interstellar medium contains. In purely chemical terms, the Golden Record could last for billions of years without any degradation. But chemistry is not the only hazard. Cosmic rays are the first physical hazard. High-energy protons, alpha particles and heavier nuclei streaming through the galaxy at near light speed, striking the probe continuously. When a cosmic ray particle hits a material surface, it deposits energy. For low-energy cosmic rays, the energy deposition damages the crystal structure of the material, creating defects, displacing atoms from their lattice positions, leaving behind a trail of radiation damage. For high-energy cosmic rays, the particle may pass entirely through the spacecraft before depositing significant energy, or it may initiate a cascade of secondary particles that deposit energy at multiple points throughout the material. Over the first 1,000 years, the cosmic ray damage to the golden record's surface is modest. The gold plating is a few hundred nanometers thick. Cosmic ray damage over a millennium would affect a small fraction of the surface atoms, leaving the record macroscopically intact. The information encoded in the grooves would be unaffected. The images and sounds could still, in principle, be decoded by anyone who found it. Over 1 million years, the picture changes. 1 million years is long enough for cosmic ray damage to accumulate significantly across the entire surface. The gold plating begins to develop radiation-induced defects at a rate that, while slow, is continuous and uncorrected. There is no annealing process, no self-repair, no mechanism to heal the damage that accumulates. The microscopic structure of the gold surface degrades incrementally. The grooves that encode the audio information, machined to depths of a few micrometers, are at risk of being modified by the cumulative sputtering effect of cosmic ray impacts, the process by which high-energy particles knock atoms off the surface and leave small pits. Sputtering rates in the interstellar medium are low but not zero. Estimates of the sputtering rate for gold in the interstellar cosmic ray environment suggest that the surface erosion would be on the order of a few angstroms per million years. An angstrom is 1/10 of a nanometer, 1/10 billionth of a meter. The gold plating is perhaps 200 nanometers thick. At a few angstroms per million years, the gold plating would last for hundreds of millions of years before being entirely sputtered away. After the gold plating is gone, the underlying copper substrate is exposed. Copper is less resistant to cosmic ray sputtering than gold. The erosion rate accelerates. The grooves themselves begin to be eroded. Over timescales of hundreds of millions to billions of years, the physical structure that encodes the information is progressively destroyed. But there is a complication. Sputtering is not the only mechanism of surface erosion in the interstellar medium. Micrometeorites. The interstellar medium contains not just gas and cosmic rays, but tiny grains of solid material. Silicate grains, carbon grains, ice-coated mineral grains, polycyclic aromatic hydrocarbons, complex organic molecules distributed throughout the interstellar medium. These particles are extraordinarily small, typically measured in nanometers to micrometers, and they travel at velocities of tens of kilometers per second, relative to any given object moving through the medium. At those velocities, even the tiniest particle carries significant kinetic energy. A silicate grain 1 micrometer across, moving at 20 kilometers per second relative to Voyager, hits the surface of the probe with roughly 10 to the negative 13 joules of kinetic energy. That is not a large number in absolute terms, but it is enough energy to vaporize a tiny region of the surface at the impact point. The impact produces a small crater, ejects surface material into space, and leaves behind a mark. Voyager was designed to survive micrometeorite impacts within the solar system, where the flux of debris is higher than in interstellar space. In interstellar space, the flux of solid particles is much lower. But over thousands and millions of years, the cumulative number of impacts becomes significant. The surface of the probe accumulates impact craters. The aluminum housing protecting the golden record accumulates impacts. The protective cover, designed to shield the record from micrometeorites and radiation, is itself slowly eroded by the same hazards it is protecting against. The aluminum housing, about 3 millimeters thick, provides substantial protection. Aluminum is a good shielding material for low-energy charged particles, and for small micrometeorite impacts. It stops many of the lower-energy cosmic rays and absorbs the kinetic energy of most of the tiny interstellar grains that strike it. The golden record behind that shield sees a significantly reduced hazard compared to an unshielded disk. But the shield is not permanent. The aluminum housing is itself being sputtered and cratered by the same environment it is protecting against. Over millions of years, the housing becomes thinner. Over hundreds of millions of years, it may develop holes where micrometeorite impacts have punched through, or where accumulated sputtering has thinned it to the point of perforation. Once holes develop, cosmic rays and particles gain direct access to the disk behind the shield. 1 billion years is a long time. In 1 billion years, the housing has been battered by a continuous low-level rain of interstellar particles and cosmic rays. The record inside has been shielded for most of that time, but has accumulated damage through the shield itself. The gold plating may be largely gone, or may survive in patches depending on the local geometry of the particle flux. The grooves are shallower than they were. The images encoded in them are degraded, but here is the thing that Sagan's committee understood, and that the engineers who designed the aluminum cover understood. The information is not stored in only one way. The aluminum cover is engraved, physically etched, with diagrams that explain how to play the record and decode the images. Those engravings are not grooves in a spinning disc. They are raised lines in a metal cover, like a bas-relief. Micrometeorite sputtering attacks all surfaces equally, but the raised lines of the engravings are more robust to low levels of damage than the micrometer-deep grooves of the record itself. The cover diagrams, the instructions for decoding the information inside, may survive longer than the information they describe. And the record itself is physically large, 12 inches across. The information is distributed across the entire surface. Individual scratches, individual cosmic ray tracks, individual micrometeorite craters, each destroy a small region of the information, but to destroy the entire record requires destroying every portion of every surface simultaneously. That requires a level of bombardment far more intense than the interstellar medium provides. The golden record, in some degraded, partially damaged, perhaps partially unreadable form, is likely to persist for hundreds of millions of years. The information it contains may be recoverable in whole or in part for tens of millions of years. And the aluminum cover, the physical object, the piece of human engineering, may persist as a recognizable artifact for longer still. Carl Sagan wrote, in discussing the golden record, that it was intended to last for 1 billion years. The materials science supports a more qualified version of that claim. Not 1 billion years of perfect preservation, 1 billion years of existence as a physical object. An existence that becomes increasingly damaged, increasingly degraded, increasingly difficult to read, but that does not disappear. That remains in some form as evidence that something built it. That someone, somewhere, once had enough to say that they chose to say it with gold-plated copper and a carefully chosen soundtrack launched into the dark between the stars. There is a specific detail about the golden record's creation that makes it more extraordinary than the list of its content suggests. The committee that assembled the record had to make choices in the face of radical uncertainty. They did not know who might find it, or when, or what their perceptual and cognitive capabilities might be. They did not know whether the finder would have senses analogous to vision or hearing. They did not know whether the finder would process information in sequences or simultaneously. They did not know whether the finder would have mathematics or physics or astronomy in any recognizable form. The decisions they made reflect these uncertainties. The images were encoded not as photographs, which require a specific decoding mechanism, but as electronic signals that a sufficiently sophisticated finder could, with effort and ingenuity, decode into visual information. The encoding method is explained on the cover. A circle on the cover represents the first image that should emerge from the decoding process, to confirm that the finder has correctly interpreted the encoding scheme. The first image on the record is a simple calibration image, a circle designed to confirm that the decoding has worked correctly before more complex images are attempted. The music was recorded at a standard pitch defined by the fundamental frequency of the hydrogen atom, the most common element in the universe, whose 21 centimeter spin-flip transition is the baseline unit of time and length used throughout the record's encoding. A civilization that knows physics will know the hydrogen spin-flip frequency. From that frequency, they can derive the intended playback speed of the record. The 55 languages in which greetings are recorded span the linguistic families of Earth's human population in 1977 with as much breadth as was practical to assemble. Most of these languages will be indistinguishable from each other to any extraterrestrial finder, but each greeting is annotated with the language's name, and the diversity of sounds represents the diversity of human vocal communication. The music selections cover a range from Johann Sebastian Bach to Blind Willie Johnson to Beethoven to Chuck Berry to Senegalese percussion to a Pygmy Girl's initiation song to a Navajo night chant to Georgian choir music. Carl Sagan advocated for including pop music and was overruled by the committee on the grounds that it might not represent humanity's best. He later wrote that he thought this was wrong, that pop music was as legitimate a representation of human musical culture as Bach. But Blind Willie Johnson's Dark Was the Night, Cold Was the Ground made it onto the record, and it is one of the most haunting pieces of music humanity has ever produced. A Delta blues slide guitar improvisation recorded in 1927 in a bathroom, because the studio lacked good acoustics. The recording crackles with age and with the reverberations of a room that no longer exists, performed by a man who died in 1947 sleeping on wet newspapers in the ruins of his house that had burned down. Dark Was the Night is Voyager's most haunting cargo. The sounds of Earth are the record's most immediately evocative content. Rain falling on a hard surface, waves on a beach, the wind through trees, a dog barking, a mother speaking to her newborn in English, a train in motion, footsteps on a gravel path. Each of these sounds is ordinary to anyone who grew up on Earth. Each of them, to anyone or anything that did not, is evidence of a specific kind of world. A world with liquid water that falls from the sky, a world with an atmosphere that moves, a world with animals and machinery and human voices, a world. Whether any of these sounds transmitted through the grooves of a copper disc and converted back to electrical signals, and then to whatever physical mechanism a finder uses to process information, would be recognizable as what they are, is unknowable. The point is not that the sounds are universal. The point is that they are evidence that this probe came from somewhere specific, that the somewhere specific has a specific character, that the beings who made the probe existed in a world with rain and wind and animals and music. The golden record is not a translation, it is a gesture, a reaching out, an attempt to say, we were here and we were like this, and we thought the universe deserved to know. Whether the universe cares is, as Sagan well knew, a separate question. The question is not whether the record will survive. Something will survive for a very long time. The question is whether any intelligence will ever be in a position to find it. The math of Voyager ever being found is the kind of math that is easy to state and uncomfortable to sit with. Let us start with the basic geometry. The Milky Way galaxy is roughly disc-shaped, approximately 100,000 light-years in diameter and perhaps 1,000 light-years thick through most of its extent, thickening toward the central bulge. The volume of the galactic disk, treated as a cylinder with those dimensions, is approximately pi times 50,000 squared times 1,000 cubic light-years. That is roughly 7.85 times 10 to the 12th cubic light-years. About 7.85 trillion cubic light-years of galactic disk. Voyager 1 is a probe approximately 3.7 meters across, defined by its large parabolic antenna dish. Its cross-sectional area is roughly 11 square meters. Expressed in light-years, its cross-sectional area is approximately 10 to the negative 29th square light-years. If a spacefaring civilization was searching the galaxy for artifacts and happened to be examining any particular cubic light-year of galactic space, the probability of Voyager being in that cubic light-year is roughly 1 divided by 7.85 trillion, roughly 1.3 times 10 to the negative 13th. If the civilization is not searching a particular cubic light-year, but is instead conducting a uniform sweep of the galactic disk, and if their sweep is fine enough to detect an object 3.7 meters across, the fraction of the galactic volume that any given sweep would cover before encountering Voyager is so small that the expected number of sweeps before detection approaches a number that has no meaningful everyday analogy. This is before considering that Voyager is moving. It does not sit in a fixed location. Over the millions and billions of years we are discussing, it traverses a significant fraction of the galactic disk. If we are generous, and imagine that Voyager's path over the next several billion years traces a tube of cross-section 11 square meters through galactic space, that tube is still a vanishingly thin thread through an enormous volume. Even a civilization that could search the galactic disk systematically would find the thread only if their search resolution was, at some point, fine enough to detect an 11 square meter object. There is a version of the detection probability calculation that makes the odds look somewhat better, and it is worth examining honestly before concluding that the search is hopeless. The version above assumes passive detection. A civilization happens to be in the right place at the right time to encounter Voyager by accident. But there is an alternative: active search. A civilization that becomes aware that intelligent life exists elsewhere in the galaxy might, upon reflection, conclude that the best evidence of prior civilization would be physical artifacts in interstellar space. The Voyager probes, and the Pioneer probes that preceded them, represent exactly this kind of artifact. They are human-made objects in interstellar space. They carry deliberate messages. They have artificial geometry and artificial composition that distinguishes them from natural objects. A civilization that believed interstellar artifacts might exist, and that decided to search for them, would face a different problem from the passive encounter case. Instead of waiting for the artifact to cross their path, they would need to develop detection methods capable of identifying small artificial objects in the interstellar medium from significant distances. The most plausible detection method for an object like Voyager at interstellar distances is radar or LiDAR. Transmit a powerful signal toward a region of space and detect the reflection. An object 3.7 meters across would produce a detectable radar reflection if the transmitting power were sufficient and the receiver were sensitive enough. At a distance of a few light years, the required transmitter power is very large, but not obviously beyond the capability of a civilization at a technological level comparable to what humanity might achieve in a few centuries. A civilization that was specifically searching for interstellar artifacts, using powerful radar systems, scanning the region around their stellar neighborhood, could in principle detect Voyager if they happened to point their radar in the right direction at the right time. This is still a needle in a haystack problem. The right direction is a vanishingly small solid angle of the sky. But it is a different kind of problem from passive encounter. It is a problem that can in principle be addressed by directed effort rather than waiting for chance. Carl Sagan's hope was not that Voyager would be found by accident. His hope was that the existence of interstellar probes would be inferred, that a sufficiently advanced civilization would reason. If we have sent probes into interstellar space, perhaps others have as well, and that this reasoning would motivate a search. Not a random search of the entire galactic volume, which would be hopeless. A targeted search of the trajectories that interstellar probes from nearby star systems would follow if such probes existed. From a star 10 or 20 light-years away, the trajectory of Voyager 1 is calculable if you know the solar system's properties. A civilization with detailed knowledge of our solar system, gathered from centuries of observation, would know that we orbit a G-type main sequence star at a distance of 1 astronomical unit. They might know, from spectroscopic analysis of the sun's light, that we have a nitrogen-oxygen atmosphere that suggests biological activity. They might conclude that a civilization producing such an atmosphere is plausibly technological, and they might reason that such a civilization, if it developed spaceflight, would eventually launch probes into interstellar space in the directions accessible from their planet. The Voyager trajectory, extrapolated backward from the probe's current position, points toward the solar system. Any civilization that found the probe and decoded the pulsar map on its cover would be able to trace its origin. But even before finding the probe, a civilization that had identified the solar system as a potentially inhabited system and that was looking for interstellar probes originating from it would know roughly where to look. This is the most optimistic version of the interception scenario. Not random encounter, but purposeful search based on inference. It requires a civilization that is thinking about the problem in the right way, that has developed the relevant technology, and that has identified the solar system as a target worth searching near. Each of these conditions is uncertain. Together, they make active interception significantly less improbable than passive encounter, though still far from likely on any specific timescale. The numbers become more interesting when you ask not about random encounter, but about deliberate search. Any civilization capable of interstellar travel would, presumably, have technology capable of detecting objects much smaller than 11 square meters at significant distances. Gravitational disturbances, electromagnetic emissions, reflected starlight, thermal signatures. A probe the size of Voyager, at interstellar distances, would require extraordinarily sensitive instruments to detect by any passive method. It emits no significant radiation after the transmitter dies. It does not reflect enough starlight to be detectable from more than a few astronomical units, even by the most sensitive current telescopes. Its thermal signature, if any remains from the decay of the RTG materials, would be at temperatures barely above the cosmic microwave background by the time it is cold enough to be called dead. The most realistic detection scenario is not remote sensing from interstellar distances, it is physical interception. A civilization moving through the same region of space that Voyager occupies at the same time would need to have, by chance or by reason, a trajectory that brought it within detectable range. What is detectable range? For an object like Voyager with no active systems, detected by reflected light, the detectable range from the most sensitive telescope systems we can imagine building might extend to a few astronomical units. For radar-based detection, perhaps tens of thousands of kilometers if the detecting civilization happened to be illuminating the region with radar. For a civilization using gravitational sensing, which is not obviously possible with any technology we can conceive of, perhaps a few light seconds. In any case, the detection range is many, many orders of magnitude smaller than the galactic disk. The probability of a civilization happening to transit within detectable range of Voyager is determined by the product of the detection range volume, and the number of civilizations times their probability of being in any given region at any given time. The resulting probability is, for any reasonable assumptions about the number of spacefaring civilizations in the galaxy, extremely small. This is the same calculation Frank Drake performed, in a different context, when he developed the Drake equation in 1961. The Drake equation estimates the number of communicating civilizations in the galaxy at any given time. It is a product of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets with conditions suitable for life, the fraction of those planets that develop life, the fraction of life-bearing planets that develop intelligence, the fraction of intelligent species that develop detectable technology, and the average lifespan of such civilizations. The uncertainties in the Drake equation factors are large. Different assumptions produce answers ranging from less than 1 to millions. But even the most optimistic, reasonable estimates of the number of spacefaring civilizations in the Milky Way, when combined with the geometric analysis of Voyager's cross-section versus galactic volume, produce a probability of interception that is comfortably below 1 in a billion for any given millennium. Over the multi-billion-year timescale of the universe, the probability accumulates. If the galaxy contains millions of spacefaring civilizations, and each of them is exploring their stellar neighborhood over millions of years, the integrated probability that one of them crosses Voyager's path at some point in the next billion years rises from negligible to merely very small, not to anything that a reasonable person would call likely, but to something that, if you run the numbers carefully, is not obviously impossible. There is one more scenario worth examining. The scenario in which Voyager is not intercepted by a random encounter, but is detected from a distance because whoever is looking knows it is there. Carl Sagan hoped explicitly that the civilization that found the golden record would be one that was sophisticated enough to understand it. Not sophisticated in a technological sense, though that would certainly help, but sophisticated in the sense of having developed mathematics and physics and astronomy to a level comparable to mid-20th century humanity. At that level, the diagrams on the aluminum cover become readable. The pulsar map, which encodes the positions of 14 pulsars relative to the Sun, using their periods as identifiers, becomes a navigational key that points back to the solar system. The hydrogen spin-flip transition diagram, which defines the basic unit of time and length used throughout the record, becomes interpretable. For any civilization that found the record and could decode the cover, the record would be self-describing. It would tell its finder where it came from. It would provide navigational information that could, if sufficient time had not passed, and if the stellar neighborhood was similar enough to the one encoded, allow the finder to identify the solar system of origin. The pulsars used in the map are real pulsars with known periods. Pulsars slow down over time as they radiate away rotational energy. The periods encoded on the record are the periods in 1977. If the record is found millions of years from now, a sophisticated finder would need to correct for the pulsar timing drift, which is calculable if the finder knows how pulsars work. The map is not permanent, but it is durable in the sense that a sufficiently sophisticated finder with the right physics would be able to reconstruct the corrections. Whether any civilization would bother to follow the map back to the solar system, whether there would be anything to find when they got there, whether the finder would understand that the record was an intentional message rather than an artifact of natural processes, all of these are questions without answers. They are questions about the decision-making of beings we cannot know, responding to an object they might not find for billions of years, in a solar system that might by then be very different from the one the record was launched from. There is a particular kind of loneliness in this calculation, not the loneliness of being alone in the universe, which is a different and perhaps answerable question. The loneliness of having sent something into the dark with the explicit hope that it would be found, and being in possession of mathematics that tells you precisely how unlikely that hope is. But Sagan knew the odds. He did not launch the golden record because the probability of interception was high. He launched it because the probability was not zero, because the galaxy is old and large and full of possibilities, and because zero is a very different number from vanishingly small, and because the act of creating the record and launching it told us something about ourselves that was worth knowing, regardless of whether anything else ever found out. We are the kind of civilization that looks at a spacecraft leaving the solar system and asks, what message should we send? We are the kind of civilization that answers that question with 116 images and 55 languages and whale songs and Beethoven and a gold-plated disc. We are the kind of civilization that does the probability calculation and launches anyway. That is not nothing. That is in fact remarkable. And so we arrive at the close of the mission briefing. The last signal dies sometime in the 2030s, give or take a few years depending on the engineering decisions made in the interim and on the way specific systems degrade. A magnetic field measurement perhaps. A number, a direction, a magnitude. Transmitted across more than 15 billion miles, taking more than 20 hours to arrive, describing the state of the local interstellar medium at a moment that will already be yesterday by the time the data arrives at the receiving antenna in the Mojave Desert or in Madrid or outside Canberra. And then silence. Voyager continues. It does not know it is silent. It does not have the category. It is a machine that moves and measures and transmits, or that moves and does not measure or transmit, but that in either case moves. The movement is the thing. The movement is what it has been doing for 50 years and will be doing for 50,000 more, and for 50 million more beyond that. It crosses the Oort Cloud over the next 30,000 years, through a region so diffuse that the crossing is statistically indistinguishable from crossing nothing. It passes within 1.7 light-years of AC plus 79 3888 in approximately 40,000 years, the red dwarf in Camelopardalis that it will approach more closely than any other star in its trajectory. The flyby is imperceptible to any instrument aboard. The star does not notice. The geometry simply reaches a minimum and then begins to increase again. In 296,000 years, the closest approach to Ross 248. In millions of years, the closest approach to Sirius. In billions of years, a trajectory through the Milky Way that is becoming progressively less predictable as more and more gravitational perturbations accumulate, until the uncertainty in the probe's position grows large enough that physics can no longer specify where in the galactic disk it is, only the probability distribution of where it might be. The golden record degrades over the same timescales. Cosmic ray sputtering removes atoms from the gold surface one at a time. Micrometeorite impacts crater the aluminum housing in slow motion. The grooves encoding the sounds of Earth become shallower, then ambiguous, then unreadable. The images fade from recoverable to degraded to gone. The aluminum cover, engraved with instructions for beings who will never follow them, persists longest, eroded but legible in its bas-relief diagrams, a set of instructions with no one to read them in the surrounding dark. And somewhere in the galactic disk, in some region of some star's planetary system, or in the interstellar medium between them, perhaps in 10 million years or perhaps in a billion, a civilization built from entirely different atoms by entirely different evolutionary pressures, speaking a language that has no cognate in any human tongue, studying a sky that shows familiar but shifted constellations, extends its reach into the space between its own stars. Maybe it finds Voyager, maybe it does not. The math says probably not. The math also says that the galaxy is 13 billion years old, and that the universe will exist for many orders of magnitude longer than that, and that the integrated probability of interception, summed over all possible finders and all possible years, is larger than the probability at any single moment suggests. If it is found, there will be a moment, a moment when an instrument on some ship or probe or station registers an anomaly. An object of artificial geometry in the interstellar medium, a probe the size of a grand piano by the standards of the civilization that built it, though perhaps by then it will be more battered and degraded, its solar system scale meaningless to minds that measure differently. The finder will examine it. The finder will determine that it is not natural. The finder will look at it more carefully, and they will find the aluminum cover, and on the aluminum cover they will find diagrams. And if they are the kind of civilization that Sagan hoped they would be, the kind that does mathematics and understands physics and has learned that the universe contains patterns that can be read, if you know the language, they will begin to read what is written there. This is the thing about Voyager that makes it unlike every other spacecraft ever launched. Every other probe we have sent has a defined mission and a defined endpoint. It goes somewhere, measures something, transmits the data, and the mission is over. The spacecraft, if it does not burn up or crash, eventually becomes debris, inert, a piece of hardware that served its purpose and then stopped serving it. Voyager's mission does not end when the signal dies. Its mission changes. The scientific mission ends. The message mission begins. And the message mission has a timescale that is not decades or centuries but millions and billions of years. It is the longest duration mission in human history. And it is one that we launched 47 years ago and that will be running when every human alive today is gone, when every record of every human alive today has been lost, when the civilization that built Voyager is as remote from whatever exists then as the paintings in the caves of Lascaux are from us. There is a specific quality to that thought that is worth dwelling on. We have sent something out that will outlast us, not by a small margin, by orders of magnitude. The human civilization that built Voyager is unlikely to persist for 1 billion years in recognizable form. Civilizations do not typically last that long. But Voyager might. The aluminum housing might still be an object in interstellar space, damaged and pitted but present in 1 billion years. Long after whatever we are now has transformed into something unrecognizable or disappeared entirely. That is an unusual kind of continuity. Not the continuity of culture or language or political institution, none of which survive for more than a few thousand years at best. The continuity of an object. A physical object that carries, in its physical structure and in the disk mounted to its side, the record of a moment in the history of a civilization that no longer exists, a message from the dead to whoever comes after. Carl Sagan wrote that Voyager's record was a bottle thrown into the cosmic ocean. The metaphor is apt. The bottle carries a message. The ocean is vast. The probability of any particular piece of shore receiving it is small, but the bottle is in the water, and water in enough time reaches every shore. We do not know what the shore looks like. We do not know who is there. We do not know if anyone is there at all. But we made something, and we sent it, and it is still going, and as long as it is going, the message is still in transit. In approximately 14,000 days, the probe will transmit its last pulse of data across 15 billion miles. After that, Voyager goes on alone, not toward any particular destination, not with any particular purpose that can be specified in advance, but into the galaxy it has spent half a century beginning to cross, into the interstellar medium that no human-made object had ever travelled through before it, into the dark between the stars that it was never designed to cross but that it is crossing anyway, because we pointed it in a direction and it went. It is still going. And whatever finds it, or does not find it, in the millions of years ahead will learn something about the kind of civilization that built it, that built something to last, that asked what they should say and then said it, that launched it into the dark with a stylus and instructions and a carefully curated soundtrack, in the explicit and improbable hope that something out there would someday be in a position to listen. The probability calculation has one more dimension that is worth adding explicitly. The question of how long a spacefaring civilization's spacefaring phase lasts. The Drake equation includes a term called L, the average longevity of a technological civilization. This term is the most uncertain factor in the entire equation. It could range from decades, if civilizations tend to destroy themselves shortly after developing nuclear weapons or equivalent technologies, to millions of years if civilizations tend to be stable and long-lived. The value of L matters enormously for the probability of Voyager being found. A civilization with a spacefaring phase that lasts only a few thousand years is unlikely to explore far enough from its home system to encounter Voyager, and unlikely to develop the technology for detecting small objects in interstellar space within that time frame. A civilization with a spacefaring phase that lasts millions of years has had time to develop the technology, and has had time to spread through a significant fraction of the galactic disk. If the Drake equation is solved with optimistic parameters for all factors except L, and if L is set to 1 million years, the expected number of spacefaring civilizations in the Milky Way at any given time is in the hundreds of thousands to millions range. Spread through the galactic disk of 10 to the 12th cubic light years, these civilizations would have a spacing of thousands of light years between them. Voyager, traveling at 17 kilometers per second, moves roughly 5 light years per 100,000 years. It would take Voyager millions of years to traverse the distance between typical civilizations if they are separated by thousands of light years. The probability of Voyager crossing within detectable range of any such civilization in the next billion years is still small, but it is not zero, and it is computable. With 1 million spacefaring civilizations, each with a detection range of, say, 10 astronomical units for passive detection of a probe-sized object, the total volume monitored by all civilizations at any given moment is a tiny fraction of the galactic volume. But over 1 billion years, civilizations come and go, and the total volume that has been monitored at some point by some civilization is larger than the volume monitored at any single moment. This accumulated probability, integrated over 1 billion years with optimistic assumptions, comes out to something like 1 in a million. Not encouraging, but not zero. What this calculation reveals is less about Voyager specifically, and more about the general question of interstellar communication by artifact. Physical artifacts are extraordinarily inefficient carriers of information compared to electromagnetic signals. A radio signal from Earth travels at the speed of light in all directions simultaneously, covering a sphere that grows at the speed of light. Voyager travels at 17 kilometers per second in one specific direction. The radio signal is more than 10,000 times faster and covers the sky uniformly. If a civilization is out there and is capable of detecting our signals, they are vastly more likely to detect our radio leakage than to find Voyager. This is not an argument against the Golden Record. It is an argument for why the Golden Record's significance is not primarily in its probability of interception. Its significance is in what it represents about the civilization that made it. The physical probability is vanishingly small. The symbolic and philosophical act is enormous, and enormity of meaning does not require probability of outcome. It requires intention. And the intention behind the Golden Record was real. That is what Voyager carries. That is what the mission briefing says is out there, moving through the interstellar medium at 38,000 miles per hour, past the Oort Cloud and past AC plus 79 3888, and past Ross 248 and past Sirius, into whatever the Milky Way holds in the billions of years ahead. A message from us to whoever is listening, sent in 1977, still in transit. There is a final thought that belongs here, at the end of this mission briefing. Not a scientific thought, but a human one. In the history of space exploration, Voyager 1 occupies a specific and unusual position. It is the farthest travelled human artifact in history. It is the first human-made object to enter interstellar space. It carries a message, and it carries the message not to any specific recipient, not to any known or suspected civilization, but to possibility itself. To the vanishingly small but non-zero chance that something, somewhere, will eventually be in a position to receive it. The people who made it knew this. Carl Sagan knew the probability of interception was very small. The engineers at JPL who designed the probe knew that the scientific mission would eventually end and that the probe would continue into silence. Frank Drake, who contributed to the design of the Golden Record's encoding, knew the mathematics of galactic searches. They launched it anyway. This is not irrational. It is a specific kind of rational, the kind that considers not just the probability of an outcome, but the value of the act regardless of outcome. The Golden Record has value whether or not it is ever found. It has value because making it forced the people who made it to ask themselves, what do we want to say to the universe? What represents us? What music? What images? What sounds? What greetings in what languages? Those questions and the answers chosen are a record of human self-consciousness in the late 1970s, a snapshot of what a particular civilization, at a particular moment thought was worth preserving and transmitting. That snapshot has historical value on Earth entirely apart from any extraterrestrial context. Future historians studying the late 20th century will look at the Golden Record as a document of what that civilization valued, what music it chose, what images, what omissions, what inclusions. The record is a historical document even if no one outside this planet ever sees it. But the intent, the explicit and deliberate intent, was extraterrestrial. The hope was that something would find it, that something would hear Dark Was the Night, Cold Was the Ground, performed by Blind Willie Johnson in a bathroom in 1927, and would not understand it, would not have any concept of the history of the Delta Blues or of the life of the man who played it, would not know what a guitar is, or what poverty feels like, or what the darkness of a cold night in the rural South in the early 20th century meant to a blind street musician, but would recognize it as a sound made by intelligence, made with intention, made with feeling, made to communicate something about the experience of being alive. That is what Voyager is carrying. Not just data, not just a message for an unspecified future finder. The record of a civilization that, when confronted with the opportunity to send something into the interstellar medium, chose to send art, chose to say, we feel things, we make music. We have sorrow and joy and beauty and the specific kind of ache that Blind Willie Johnson put into his guitar in a bathroom in a southern city in 1927. We made this. We are the kind of thing that makes this. The probe moves through the interstellar medium at 38,000 miles per hour. The music moves with it, encoded in the gold-plated grooves of a copper disk, degrading slowly under cosmic ray bombardment and micrometeorite impacts, present in the dark between the stars, not heard, present. That is the mission. That is what the silence inherits. And there is one more thing to say about the Golden Record before the close. The record was not the first time humanity sent a physical message into space. The Pioneer 10 and 11 probes, launched in 1972 and 1973, each carried a gold anodized aluminum plaque, designed by Carl Sagan and Frank Drake, with the artistic assistance of Sagan's then-wife Linda Salzman Sagan. The Pioneer plaques are smaller and simpler than the Golden Record. They show a man and a woman, the figure of the man raising a hand in greeting. They show the solar system and the probe's trajectory through it. They show a diagram of the hydrogen spin-flip transition to establish a unit of time. They show a starburst diagram of pulsar positions to identify the solar system's location. The Pioneer plaques provoked some controversy at the time. The naked human figures drew criticism from readers who found them obscene. The woman's figure was criticized for appearing passive while the man raised his hand. The inclusion of human nudity on a spacecraft was debated in public, with NASA receiving critical letters and some news coverage treating the decision as scandalous. Carl Sagan was undeterred. When the Voyager mission came and a larger and more ambitious message was proposed, he advocated aggressively for the most comprehensive record possible. The Golden Record was the result. More ambitious, more beautiful, more comprehensive, and more carefully designed than the Pioneer plaques, it represents the fullest version of what Sagan believed humanity owed to the possibility of contact with another civilization. The Pioneer plaques, for their part, are still attached to Pioneer 10 and Pioneer 11. Pioneer 10 is heading toward the constellation Taurus and will pass relatively near the star Aldebaran in about 2 million years. Pioneer 11 is heading toward Aquila. Neither has the scientific instrumentation to return data at this point. They too have gone silent. But they carry their plaques into the interstellar medium on trajectories slightly different from Voyager's, extending the thin distribution of human artifacts scattered through the nearest interstellar space. We have sent 4 probes into interstellar space: Voyager 1, Voyager 2, Pioneer 10, and Pioneer 11. Each is carrying some version of a message. Each is on its own trajectory. Each is moving away from the Sun at roughly similar speeds, though in different directions. Together they constitute humanity's physical presence in the interstellar medium. 4 probes, 4 messages, 4 trajectories through the dark between the stars, moving at speeds that will carry them past their first stellar encounters in tens of thousands of years, and that will keep them moving through the galactic disk for billions of years after that. The universe has 4 points of evidence now that something on the third planet of a G-type main sequence star in the Orion arm of the Milky Way once looked at the night sky, built machines, and sent them outward. Whether it ever finds those points of evidence is the open question. Whether the asking matters regardless of the answer is not. Strap in, keep looking outward, and stay with the crew. If you want more mission briefings like this, subscribe for the next journey.